We can state the second assumption, strict exogeneity, as follows. So write the expected value of epsilon, the column vector of error terms, under the condition that I observe the data matrix, and this is supposed to be equal to the all zero vector. Note that equation 1 uses column vectors with dimension n times 1. Hence the equation states for n observations from I is equal to 1, 2, up to capital N, that the conditional expected value of the error term epsilon I, given that we observe the data matrix, is equal to 0. The condition that we observe the data matrix means that all the values of these k variables plus the constant are known. So we don't treat them as random variables. To understand equation 1, we need to discuss expected values, or to be more precise, the expectations operator E. Introducing expected values requires a few more concepts, including random variables, probability mass functions, and probability density functions. A random variable, say capital Z, is random in the sense that the outcome differs between different states of a world. So note that we refer to a probabilistic nature. There's a lot more to discuss. For instance, states are mutually exclusive to make our approach more rigorous. For instance, rolling a dice and defining Z as the outcome of a single roll suggests 6 states of a world with a state space omega. So omega would contain the outcomes simply 1, 2, 3, 4, 5, and 6. The random variable Z only takes discrete values. Thus, Z is a discrete random variable. If a dice is fair, each outcome, each state, has the same probability. So we can state the probability of Z taking a value Z is equal to 1 divided by 6, and Z would be an element of my state space omega. We further have the condition that probabilities should be positive, and summing over all the outcomes, these probabilities should give 1. We have to demand that probabilities cannot be negative. They can be 0 but not negative. And second, when we sum over all these sets in the state space omega, these probabilities sum up to 1. The second condition implies that the state space is complete. Now, taking the expectations operator yields the following. So I take the expectations operator for my random variable Z. In this case, Z is a discrete random variable. So that means I sum over all the sets in my state space the outcome Z times the probability that this set occurs. Now in our example, this is quite straightforward. We have all the same probability here, and then it would be just the sum of the outcomes. And I should get 3.5. Now let's consider a continuous random variable, say p, where p can take any value in the closed interval from 0 to 1. Closed interval means that the boundaries are included. So p takes values in 0 and 1. All outcomes are equally likely. Hence, p is a continuous uniform random variable with probability density function fp is equal to 1. Now again, we require that fp, so our probability, it's not quite the same, is positive, and summing up over all the possible outcomes, all these probabilities should be equal to 1. Now we are in a continuous case, so we have to integrate. In our case, we go from 0 to 1 over the density function dp is equal to 1. Now, taking the expectations operator yields the following. So the expected value of p is now the integral from 0 to 1. The outcome is p, and then fp refers to the probability density function, and I integrate over p. The density function is equal to 1, and that here would integrate as follows, is 1/2 p squared 0, 1, and I would get 1/2. Again, if you have any questions, let me know. There's always a lot more to say, but I try to keep it as simple as possible. But still, I want you to really understand where different things are coming from. Now we have an initial understanding of discrete and continuous random variables and the probability mass or density functions. In addition, we know how to calculate expected values in both cases. Finally, the conditional expected value suggests that we can take all explanatory variables as observed values. They are not considered to be random variables. We will spend quite a bit of time on strict exogeneity and derive further implications in the next videos. I see you there.